So Pierre Fauger will present an application of a local approach model with a model which is called MIBF, for microstructure informed brittle fraction. For several years, this model has been developed at CEA. Its characteristics are a description of microproduct initiators, such as carbide, a Griffith-like behavior for pH, the crack initiators, a weakest link hypothesis. So that's similar to other local approach models like GRIFFITH, etc. But we have also a description of a local stress distribution sigma star inside an elementary volume due to the microstructure of the model. I will explain this here. In a classical local approach model, suppose you have a specimen which is loaded, CT specimen with a P, loading of the specimen. You have a crack tip, you have elementary volumes. Inside these elementary volumes, V0, you have carbide with different size. This volume is loaded at stress, macroscopic stress sigma, and carbide will gradually can propagate according to Griffith's criterion. So this is very model. In MIBF, we take into account the magnetic microstructure, and we consider that the local stress distribution sigma star inside V0 is not uniform, but will be distributed around the mean value sigma. So this was computed using crystal plasticity aggregate simulations, which were performed on the virtual magnetic microstructure. Due to grain orientation and incompatibility of deformations between grains, the stress field inside V0 is heterogeneous. And for our application, we use this kind of simulation to fit an analytical function that will describe this heterogeneity of stress within the volume V0. We chose a variable type function of this type. For example, let's suppose that the principal stress applied to V0 is 1,200 megapascal. This function will tell us that approximately 75% of the volume will see a stress that is higher than 1,000 megapascal, only 75%. And 15% will see a stress that is higher than 1,200 megapascal. So 15% will see a stress that is 1,300 megapascal. Now, let's come back to the carbides. When we use the Griffith for microcrack propagation, we have here the value, parameter, which is the surface energy, and this will be the only parameter that will be fitted on fracture toughness test results. All over are fitted on crystal plasticity computation or on the carbide size measurements. So, to summarize what we can see inside the material, a failure of one carbide of size R, which is loaded by a stress sigma star, will be given by the variable function applied to the value of the Griffith criterion. If we have a carbide of any size within V0, we have to integrate over size R and take into account the size, carbide size distribution. If we have not one carbide but NC carbide per volume unit, we'll have this expression. And for the specimen, we have to integrate over the plastic volume. Now we can apply MIBF to near steel. We used Euro material A, for which it's a German steel, for which we have, of course, stress-strain behavior. We have carbide size distribution and fractal toughness results. For this result, we'll use only pure cleavage results to apply this cleavage model. Metallographic analysis on the Euro material A were performed by Serco and Arva, Germany. We counted the carbide in the volume unit on the metallographic views. They measured the carbide size of each carbide. From these counts, we can determine an experimental carbide size density distribution, and we will fit a carbide size density function, which is also a variable type distribution on this on the experimental results. Now we have all we need to calibrate MIBF model. MIBF was calibrated on the RTCT specimen at a temperature equivalent to the Mostocker reference temperature. And then we made computations for different temperature and different size of specimens, CT specimen. And we see that globally we have a satisfactory prediction from, say, T0 minus 50 degrees to T0 plus 50 degrees. Now we can make represent the same results on the K versus T diagrams. And if we include other higher temperature results, we see that we still have a satisfactory prediction at higher temperature, but only concerning low float ties, so we're very indicated. Now, what is interesting with MIBF model is that we can evaluate the contribution of each carbide size to the failure probability. Using this approximation, we can rewrite the equation of the model. And in this equation, we have in black the total number of carbide inside the plastic volume, given as a function of the carbide size, so the black line. And in red, the carbides that contribute to failure for a given loading. The proportion of the carbides that will contribute to failure. So I will plot this curve for different loading. Here, if we consider the carbide critical carbide size according to Griffith criterion, on the right you have all the carbides that would all the carbide sites that would have been activated if we didn't consider crystal plasticity effects. So like in pyramid model. And on the left, here, you have all the smaller carbides, carbide sites that are activated due to the stress amplification generated by crystal plasticity. So I will represent this curve for different loading. As the stress intensity factor increases in the specimen, of course, the carbide involved in the failure gets smaller. Okay. For a given loading, say for example for the blue curve, if we look at big carbides, say carbides of 1 micron, all of them contribute to failure. Although they are very rare, if they ever exist. On the contrary, for smaller carbides, for example, 0.4 microns, which contributes the most to failure, only a small proportion of this carbide contribute to failure, with a proportion of 1/1 million inside volume, plastic volume. Now, if we compare two different temperatures, with a lower temperature, we see that the carbides involved in failure at lower temperature are smaller than at T0, and above T0, I would have almost the same curves. Now, in the gray point here, represent the experimental metallographic carbide analysis, and you see that most of the carbide sites that would have been activated due to Bermin model without plasticity, without crystal plasticity, are of a size higher than what we can observe on metallography. On the contrary, the smaller those carbides that are observed on metallography can be involved in failure due to the dispersive effect of crystal plasticity. So, in conclusion, well, MIBF is a model which uses some microstructure characterization of RTB steel, so microstructure effect on the stress distribution and the size distribution of receivers. It has been calibrated on an RTB steel with only one parameter, which is calibrated around T0. We obtained the model was validated at different temperature in the cleavage domain with a reasonable size effect prediction. One important point is that we don't need to introduce any temperature dependency on effective surface energy. Contrary to Bermin, where we are often obliged to consider a dependency of sigma u versus temperature. This model, the role of incompatibility stresses due to crystal plasticity has been highlighted. This role widens the range of carbide size implied in the fracture process. We saw that most of the carbide size are involved are larger than what we can observe in the metallographic analysis. So it would be important for future metallographic analysis to characterize a larger number of precipitates, maybe several thousand instead of only several hundred tons. Last point, there are some possible extension of MIBF model, especially concerning grain boundary effect with intergranular carbide, possibly leading to modelization of intergranular fracture, or other type of population of defect, multi-population of defects. Thank you.